these areas. Yeah, like I said. Easy to follow. Okay. You see my screen? Mm-hmm. All right, thank you. Good morning, good afternoon, everyone. My name is Antoine Segnegon. I'm an application engineer here at Altair. Today, I'm going to briefly talk about RADIOSS and basically do a little demo on how to set up a basic crash model for, let's say, a full frontal and back in RADIOSS. I have one model we will go through, how to start from creating material, all the load cases, and then run the analysis. I have already the model ran and the result. We can interpret the result later on. So this will be an interaction section. So if you have any question, let's talk like we are in the class. Thank you, and we'll. There it is. Okay. So we start with I put a brief agenda together, what we will be covering or what I will be showing. Because of the time and the model size, I kind of go demo how to create a material, how to create a different set, and then if you have a question, we can follow up. What we want to cover here is what is RADIOSS first, and then we highlight some of the capability of RADIOSS. Then we do a demo at the end and follow with question. What is RADIOSS? RADIOSS is an Altair software. It's a solver for highly nonlinear problems on the dynamics loading. It's very highly scalable. In any number of core you run, RADIOSS can give you a great performance. It also have a very high quality. It's very robust. They also support multi-physics simulation. They have many different advanced material model, failure model criteria. We also have RADIOSS used across many industry. I will briefly give you some of different industry where we use RADIOSS. It's been in the market for over 20 years. Very compatible. It has very high and efficient result when you use your analysis. If you look at the overall where RADIOSS is mainly used, using crash analysis, and today's demo will be focused on crash model setup. It's a full frontal model setup, and then we also show you a little bit of a pole impact model. Also using drop test, blast or ballistic analysis. RADIOSS is also used for fluid structure interaction. You can use it for thermoballistic analysis. You also have high performing for composite. You can also map in RADIOSS. So it's really a multi-physical analysis and used for high optimization tool. If you look at the different area where we use RADIOSS, I mentioned about crash. You can see on your left side here where we have frontal and back offset. And railroad industry, RADIOSS is also used. You also use RADIOSS for occupant airbags for analysis, and also dummies. There are many dummies for RADIOSS. We have barriers also developed for RADIOSS, and these applications can be used for short duration crash and transportation system. We also have RADIOSS is used for impact such as drop test. You can also see a simulation where we do a smooth hydrodynamic particle analysis, SPH. And so RADIOSS can be used in all these different type of applications that you can utilize. So don't be limited to any, even though we talk about crash today, we shouldn't be limited to crash only. It has many areas where we can use RADIOSS. If you look in there, I've mentioned about fluid structure interaction. You can see a boat ditching. You see an airplane ditching in the water. So the water can be modeled here as a SPH and also ALE. and you can see bird strike analysis, for example, where your bird is design or model has a particle. You can also see fluids, this fuel tank is slushing. We can use RADIOSS in those kind of applications. If you look at your right side here, the slushing here, we use a particle SPH for this type of slushing analysis. For blast analysis, we have you can use RADIOSS for blast, ballistic analysis, high speed and impact, for military application, and also for explosive mechanism. You can use RADIOSS. You can look on the right side here where you use RADIOSS, and also apply some failure criteria for these type of analysis. Material characterization, we also design RADIOSS and do material characterization where we can identify the material. We can also include a different composite material we do have available. You can see on the left side here where you see a failure criteria. These are representing things you can use for glass analysis. You can also use for foam or barrier analysis. We can use those for RADIOSS. RADIOSS is also used for stamping. We have a design stamper for stamping analysis where you can do hard forming, wave composite draping, and also metal cutting and hydroforming. RADIOSS is also used in this type of area. To be not to just be limited on those areas, I just wanted to focus today. The intent today of the webinar is to put together how we set up a simple model in using RADIOSS and set up an analysis and then look at the result and kind of interpret the result. But before that, we wanted to give you an overview of what are the different areas of industry RADIOSS can be used. So today, what we wanted to set up is a simple model. Here we took a NEOM model, it's a public domain model, and then we want to run this model for about 35 miles per hour. So what we want to do is how to set up this model in RADIOSS. So Altair have many tools. We mainly have two preprocessor tool that you can use to set up a RADIOSS model. You can use HyperMesh, which is designed for all the application. It could be RADIOSS, could be any solver, Abacus, Dyna, and so forth. And then we have another tool in-house, which is called HyperCrash, which we use mostly to design for crash analysis. That means, say, you can use that for other things, but mainly concentration on crash analysis. So that's what we wanted to use today on HyperCrash. The demo will be focused on HyperCrash, how to set up the model in HyperCrash environment. Okay, so I'm going to stop my PowerPoint from here, and then we're going to move to the model setup and how to create material, how to create a section property, all the other features that we wanted to add, such as interfaces, monitor volumes, and so forth. So, but what we do on the HyperCrash, we first launch. I have a model called NEOM-based model. We will import this model into HyperCrash, and then we'll set up this model. I already have a pre-set up, but I'm going to show you how is the setup by showing things like how to create material, input the parameters, and so forth. So we're going to switch from the PowerPoint to the demo kind of stuff. Any questions so far before we go further to the demo?
Antoine, currently there aren't any questions in the question window. We'll give a couple seconds to see if anybody has one, but I suggest we move on, and then if there's questions come on, I will interrupt you.
Very good. Thank you, Darius. So once you have your HyperWorks package, you launch HyperCrash. You go under the program where we install the HyperWorks. You go here, and I say I take HyperWorks 14, and I have HyperCrash. This window will pop up, It's where I'm going to launch the HyperCrash. I can select my working directory here. I already set up. I set for my webinar. And then I select the version, or I would say the server version. In this case, I say RADIOSS 12. But if you click this arrow here, we have many different versions. I mean, you also have Dyna, Crash, and then we have RADIOSS here. So we launch, say, we work on RADIOSS 12. Means the server 12 version. And then here we have the unit system that we can select. In this unit system, you have many systems you can select, and so forth. So based on the information I have in the model, my unit system is what I have. I pick Newton, millimeter, second, and ton as my unit system. And I hit run HyperCrash. So my HyperCrash window will pop up. So from here, I will go and import my model. So import the RADIOSS model, and I will pick these model that I want to build. So basically, how do we start from? This I already have the FEA model, which I'm loading the FEA model, but basically to set up a crash model, you get the CAD data from the design release engineer, and you are going to mesh, discretize all those components into your FEA to create a FEA model. So after the meshing, which we use HyperMesh to do the meshing, then we use here, we can use HyperCrash to build a model or HyperMesh to build a model. In this case, we use HyperCrash. So you bring your FEA model. This FEA model normally should not have any entity such as material and property and so forth. But because of the time, I already built this model with all the material and property, but I go and step by step, how do you create the material and property? So basically, you launch your model here, and you will have the model tree where all your assembly are organized. Here we have the wheel assembly. If I show this, I have my wheel assembly, and then my model browser to tell me what are the different entities I have in the model. Okay, so in RADIOSS or any other tool, you have a part. So every part should have a material property, and then also a section property assigned to the part. That's how you can monitor the stiffness, your behavior, failure criteria for the part that you are dealing with. So each part will have it. So in this group, we get the FEA model. So from the starting, you should start creating the material. So we start creating material. We go on the model in the HyperCrash, on the model, and I have the list of material. You will see a many list of material here, but I can create a new material. Okay, so to create a new material, I go here and I say create a material. Elastoplastic material, I can pick up a Johnson Cook material, and then HyperCrash give me this window. All right. So here I can input all my material information. Put the density here. I can say maybe 7.8 minus 9. And then I can put your Young's modulus. All right. Then I can put the Poisson's ratio. 3. I can put the yield stress. So let's say maybe I'll say 92 megapascal. And then I can put the right. Then I can put the okay. So I have the basic parameter to put, and then from here I need to select the part that I will assign this material to. So I can go here and my right mouse click here, and I say, let's say I pick up the rear windshield, and I go here. So now, if you can see on my list here, the material I just created, called new material 808. If I display this material, it told me the material was assigned to this part. I can look at the stress strain curve for that material. So HyperCrash, I click this icon here, it shows me the material property that I put, if it makes sense to me. So these things should be checked. So now I have my material created. I can create another material and assign to different part in the model. Okay, so now my material is there. This material I can assign to the failure criteria. For the time being, I won't go to failure criteria. We can leave on the failure criteria, but I leave the simple material without any failure. Okay? I can have, if we want, I can define maybe a failure criteria here through plastic strain. If I put the maximum plastic strain value here, let's say maybe 10%. If I put 10%, any element that will reach this 10% will have a failure criteria. Then I'm satisfied. I say, okay, if I agree with this, I can save it. I have my material assigned. Then the next thing I need to do is to create also a section property for that part. Okay, I go to the same thing, the surface, property type, say 1, and this, I put the thickness of that part, let's say maybe 2 mil, all right? So I have my thickness, and then these are the thickness variation and plasticity information that I wanted to set. If I set to 1, the thickness will vary during simulation. If I set it to 0, this means the thickness stay constant, no change. Same goes for the flag for shell plane stress. Okay, so for the time being, I leave it as it is, and I can define the number of integration points. Let's say maybe 5. I define number of integration point through thickness, meaning the 2 mil here will be divided into 5 layers, and then my analysis will be run based on those 5 different layers. So if I am satisfied with this one, I go to right mouse click, assign to this part, and then I say I have my material created. He say the change request may affect the connection because this is connected. I say, yeah, do you want to modify? I say yes. Because in my building, I already have connections such as hardware or type 2 interface for these one. So now I have my property created. I have the material created for this windshield. That's what all the entity in your, all the part or connector in your model should have. Now, in the model, you will have 1D element, 2D element, this is a 2D element, and 3D element. In RADIOSS, some of your stiffness for 1D element are in the section property. So if you have a spring element, you won't have a material assigned to a spring element, but a property for the spring element. That's where your spring element stiffness will be. So that's what we'll be saying for material and property creation. Okay? So now we have all these. So all my model, you can see I showed some dotted blue here because when I change this material property, these connections, which are the spot where are affected. That's why you see them on the screen. So I can just turn them off and just it. So every component I have will have material and property assigned to it. Okay? So I move into the next step. What else I can do, because I'm building the model, I already attached all these models. You can do attachments through spring element. You can do through rigid body. You can do through beam and trusses. So these will have all the attachment. You can see here some of the attachment are there to a complete model. So the first thing, material, property, and then assign to a part. That's what we just did. That's what you'll do. So every single part will have property and material assigned to it. Then the next thing we do, what are the other entities we create? We have some tires here. We also have some, we are going to, what type of analysis are we doing first? This vehicle, we want to crash against the wall. So I have already created all my part with the property and material. Then I wanted to create a wall, a rigid wall, because the vehicle, so your vehicle should have a floor. It should have a front wall if you want to do a full front and back. That's what we're doing here. So I wanted to create a full front and back wall. Then I also have, I mentioned earlier about the tires. These tires, right now, those tires will not have air inside. I create few tires with air, but I'm going to show you how we create air for the other tire. Inside the tire, we call monitor volume. That's why we basically nothing but the air bag. So these air bag will be put in this volume, closed volume. So I'm going to do here, I want to create monitor volume on the other tire, this one. So I go here and say monitor volume is a tire model. So I put a tire, and then I just put the surface that I want to click. So what I want to click is, I pick this volume, it has to be closed. And then I put the pressure, scale factor. I also can put the mu value here, the gamma, put 1.4, mu, let's put 0.13. And then bursting pressure, I can put the 0.03. Initial pressure, I can put 0.01. Okay, so this I assign to this tire. It should be closed. Okay, yes. So my selection here, I also need to add this part. So otherwise the volume will not be closed. And if I'm satisfied, okay, I have my monitor volume created. If you look at the monitor volume now, I have the all the monitor volume are created. So these are tire. I put the initial pressure and the bursting pressure and also external pressure on here. So now these tire will be act like a physical tire model. Yes.
So the question is, for the values that you defined there, where would they find values for that, or should they use the values that you are using for your tire model?
Okay. Basically, the value we are using here are, let's say, in a tire, vehicle tire, how much pressure you have. Let's 32 psi. So we are using this value that you convert, you put it into the, and then the gas constant, which is the gamma, the gas constant. Those are the physical gas constant that you calculate based on the air pressure and so forth. So you put those values into your tire. So now, once that tire reach that initial pressure or reach that bursting pressure, you'll see the tire will be deflated. You can also use different options to deflate the tire. Okay, let's move on. So I have created material, and the next thing I say, okay, I have all my tire. I want to make sure they have air inside. If you have a spare tire here, you also put air spare in the spare tire in case you do a real impact. You want to make sure that spare tire is there. So you define those. Then the next thing I wanted to do, I also have different features in building the model. If this model is, let's say when I'm assigned a job, you get to a job, the supervisor say, okay, do a frontal impact for this model. You may have all the parts already available for you. You may also have some part that you are grabbing from a CAD, you mesh, and you want to add in here. So to do those, we have different options in HyperGraph. Things like part replacement. Let's say I wanted to replace this bumper. Okay? Because this bumper is maybe the older bumper, and I have a new bumper that I wanted to add it to. So what I do here in HyperGraph, I can go here and I select this bumper. I display highlight the bumper only. Let me clear my volume up so I can. Then I have the bumper. I want to change this bumper to a new bumper. I right mouse click here and I say replace. Say replace the mesh, my mesh. I go here and I can pick up, I say front bumper, meaning a new bumper that I just got it from the design release, and I mesh it. I want it to replace here. So I go and HyperGraph will come and replace it. What HyperGraph will do, it will show you this part. It will tell you this part that you are replacing, there are different entities that were affected. Your surface will be affected because when this part is already in a contact, so the contact is going to be affected. They also tell you the time history because that part was put in the time history before. It will be the time history information will be affected. You wanted to put all these in the time history and also make sure the section surface are updated. You say yes, and then you close the volume. So now, if you look at this part and interrogate this part, what was the attachment connection to it? It shows you this part where prior to that it was connected by spot weld. So we get you all this information, and now you have your part replaced, and HyperGraph did connect the part because the part you are replacing used to be connected. Okay, bring all the model up. So now it displays you all these parts that were affected during that process. Okay, another thing we do also beside the part replacement, let's say I don't want to replace the part. I can merge a part. I have this door part, for example. Now I'm bringing a new door. I'm not replacing, because when you replace, you are using you are taking into account all the entity associated to this part you're replacing. Things like material property, section property. Those things will be using the existing part. But if I don't want to use the existing part, material information, I can merge, bring a new part into it, such as door. You can do a merge. In order to do the merge, you go to File, Import, and then you say RADIOSS. Then you click the word merge. I won't do the process here, but you do merge. Then you bring a new part into it. In that case, once you do that, what you need to do next, you have to add this merge part into all the existing entities, things like initial velocity, things like contact. So you have to add those again, which is slightly different than replacement. Okay? So that's the part. You can also add mass. Because what we have in the FEA, we do have a FEA model. We simplify the FEA model. If you look at this one, it doesn't have all the vehicle content, right? You see the light are missing. You see a fuel tank. I mean, many parts are missing. Okay. So those parts that are missing, you need to make sure that the mass or those are implemented into this full vehicle, because you are going to compare it against the test model. The test model have everything, things like small trims and all these that you can mesh here. You can mesh them, but you will have an effect on the size of the element because they're so small. In the explicit scenario, you will have time step issue, for example. So those parts that are missing, you can add a mass to compensate those entities. So we go to load case, and I go to add mass, I create new. Let's say I want to add mass to the node group. I want to add mass to the area. I can select all these and say add mass and distributed mass. Let's say on a single part. And I select this part, say the door, and then it tells me what are the mass value. I can add the mass here, volume, and then I can put the values here. Let's say I put 10 kg. So if we put 10 kgs and I save it, what HyperGraph will do, the preprocessor will do, you can see those yellow node. It take all the single node of those parts and it distribute this 10 kg within those 1,000 nodes. So you divide the 10 kg by the number of nodes, and each node will have the value that you find. So we'll add it to this one. That's how we add mass to compensate the missing part that we did in our mesh. Okay? So to add the mass, those are some of the features we can add. The next thing, so different feature that we have available. Let me see what goes next here.
While you're switching over, there was a question that came in, and the question is, why is the element size different in different assemblies? I'm assuming he means in different parts of the model.
Okay. Why the element size are different?
Different parts of the model, yeah.
In different part of the model. Beautiful. You see on your FEA, you do an approximation, and element size depends on the geometry. Okay. Sometimes you have a very complex geometry where sometimes you have a hole, and you need to model those holes. If I give you an example here, let's say in this tire you have some holes here. A hole is maybe a 2 millimeter diameter, okay? And you wanted to represent that hole 2 millimeter diameter. So what you have to do, you need to measure around those 2 millimeter diameter. That will dictate your smaller size of the element for this scenario. In the other area where you don't have the hole, you have a nice geometry. Your mesh size is it could be larger. So the mesh size is not a fixed size for mesh. We do, even though some company have mesh criteria. We say average mesh size could be 5 mil. That's your average mesh size. So your sheet metal may have an average mesh size of 5 mil, but some area where you have smallest element size, a smaller size, small holes, and you wanted to capture those, you violate pretty much your 5 mil element size to a 2 mil element size. Those are some of the scenarios where you could have a different size of element, and that will affect, again, play with your time step.
Yes, but the key thing there is if you use too small of element size, that has a negative effect, correct?
Yes. Too small will have a negative effect because your explicit scenario is based on time step. And time step is based on element size, where, for example, the time step for element is your smallest size length, which cannot be the small element, divided by the sound speed of the material. So yes, smaller size will affect your time step.
The key there is use as big as element size as you can for
yes.
your.
So in the explicit, you want to stay within 2-3 mil. We recommend about 5 mil, but you can't meet all that 5 mil most of the time. But you want to stay within 2-3 mil. You don't want an element size of 1 mil or 0.1 mil. So when you finish meshing, after you finish meshing your model, you need to check the mesh quality in HyperMesh, for example. You check the mesh quality, HyperMesh will calculate all the smaller size element, and they give you the smallest size element in the model. You can identify that model. If it's a 0.1, you say, no, I'm doing an explicit analysis. I cannot manage 0.1 element size. I need to change that element size.
But if you're, for instance, doing a really small model, like in this case, this model is probably closing in more than 500,000 elements. But if you were just doing a frame, which might only have 20,000 elements, if the element size is smaller, that's okay because it's just you're also having less elements, right?
Yeah. Let me emphasize a little bit about the smaller size. When we talk about FEA final element, it's really a basic approach. It's an approximation size. Okay, so we approximate to meet the physics to be reality. In order for you to have an exact or a pretty good approximation, you need to be closer to the physics, meaning I need to capture all the element size. But what happened with capturing all the element size is the turnaround time, the result. When can I get the result back? Otherwise, the best approximation is to have capture everything, have the smaller size element, but you need a huge machine. You need a bigger machine, powerful machine to run this job so you can get the result overnight. But if you don't have a powerful machine, then you need to make your element larger so that you can get the result sooner. Okay. Nowadays we can see a full vehicle model for 5 million element, and we tend to shoot for over about 10 million size element, because what we wanted to the industry is leading towards is to have one model, a common model for all the vehicle, all the impact mode, meaning durability, NVH, and then crash. One model for all. So these different attributes have different type of element size. Okay, but I think we are getting to that level where we have high speed, and that's why in RADIOSS also, if you look at the performance thing I mentioned earlier, we have different type of performance approach, MPP, hybrid MPP, and you can run many cores with your model and get the results sooner. Okay, we can move on. Let me see so we talk about the different feature, monitor volume. We have cleared that. Now we want to talk about connection. So now we add a mask, right? We also talk about, we can talk about connection. How do I connect all these things? You can connect these through all your model. You can connect through 1D element. You can connect through, if you look at the connection here, we have spot welding, we have bolt, we have glue, hemi, and so forth. Then also we have the 1D elements such as rigid body, rigid length. We also have spring, and you can all do your connection on them. So what I wanted to show briefly here is on some of the connection are, let's say, spot weld connection. So I can do a spot weld creation. I go to spot weld, and I say create. In order to create a spot weld here, I'm going to take two parts, and I wanted to spot weld those two parts. Let's say what a part I have here. I take this part, and then I wanted to spot weld it. Do a fake here. So my spot weld, what is it asked me? I'm giving an example of what you create a spot weld. He asked me first select the two parts that you want to spot weld it. Again, one part and second part. Then if I have already a spot weld created, HyperGraph will show me those parts that I've already created. I'm assuming that I don't have any spot weld created, and what I could do, you have different options to create spot weld through element selection, through node selection, or through a line, meaning you pick one point here and pick a next point, and you have a spot weld created. Or automatic also, and you select the part, the two part, and it automatically is created. Let's go spot weld through element. So I pick up the element. I already select the part. I want to spot weld here. So you can see how simple, how user friendly it is. I just select the element, and then HyperGraph, what it does, it pick up this element, it select a spring, because the spot weld is nothing but a combination of spring and two tight interface. Tight interface are meshless connection. So if you can see, here's an example. I select these elements. HyperGraph select pick up the node. It pick a slave node of this spring and glue it onto the mass on the central mass of these elements. And then it project normal down to the next element below, and this spring have stiffness. So this, you specify the stiffness here. You can have a failure criteria for your spot weld and so forth. Then you save this. Now you have your spot weld created. That's how you spot weld the whole model. You can spot weld everywhere where you think you are spot welding. Okay. The next thing we have to do, or we also have besides spot weld, we also have a glue. So glue is nothing but, as you can see, it's the same scenario as spot weld. The only difference between the glue and the spot weld are the stiffness. So glue is a lot more softer than the spot weld. If I look at this spot weld I created earlier, I can go back to the spot weld, and I want to see the property of that spot weld. Spot weld, modify, and I go pick up these. I pick up this part, say show me the spot weld. Then I pick this spot weld that I had created, and I say show me that spot weld. Let me go back up here. Say see, show me the spot weld, and then this spot weld I want to see the property of that spot weld. Say see. And then HyperGraph show me, here's the property of those spot weld. So this spot weld have the stiffness, mentioned it to you earlier. So that's the stiffness, the spring stiffness, that between. So we give you all the degrees of freedom of the stiffness of that spring, huge. All right? So that spot weld has information and property information, this one. Okay? Question, yes?
Okay, so we have a question. They would like to know, can a joint be created in HyperGraph that acts like a revolute joint in the steering axle?
Yes, joint can be created through the joint. We create the joint through property. So we go to the property type here. If I go to the property and I want to create one type of property, it's gonna, if you look at here, it will give me joints. I have spring, different type of joint. Here, I have a spherical joint, revolute joint. If I click in revolute joint, I can create those things with all these different type of joints. So we have many type of joint that are available. You also have some K joint, and then so different type of joint that are available. We can create those in HyperGraph.
Excellent. There's a question coming about friction connection or contact, but I'm pretty sure when you talk about your interfaces, you're going to cover that. So we'll hold off on that, the one question that was just asked too. So, but yeah, thank you, Antoine.
Good. Thank you. Now, I'm going to say that to touch up, not really touch up the question, but I'm going to briefly touch up a little bit. I mentioned the connection earlier, spot weldy and so forth. There's another connection that we have in RADIOSS, which is a tight connection. In tight connection, we use this interface type 2 to do the tight connection, which is the meshless connection. So this type 2 interface, I'm going to give you an example here. So under my connection creation here, I have is a kinematic condition type 2. Okay, this type 2 is pretty much like a spot weld. So what it's going to ask me here, it's going to ask me the node I wanted. Let's say I pick up the node. I'm going to pick this node. Okay, that node I wanted to connect to the segment below. So I'm going to say pick up these. So it's going to project. So what I'm doing here, you see, is a meshless connection. You don't see the spring. Okay? So what it does is kinematic. So this node here is going to be tied to this element below, any of the element below. So basically projecting this below. Now that is a kinematic. But the kinematic connection, you can switch that from kinematic to penalty. Okay? In RADIOSS. So here you have the flag. So you go here, I have the flag here where I can switch, because kinematic is like use glue. You can't do anything, you can't create stiffness, anything, but you can change that kinematic to different type of connection under the type 2 interface. You can do penalty, and then you can also have a failure criteria for that type of interface. So if you do penalty, then you can have a friction. Or if you create an interface type 7, you can also have the friction part into that one.
You just showed them the friction.
Yeah. on the type. So I save this one, and then I want to create let's say for connection I could have a load case interface. I'm on the interface. If I create a type 7. Under the type 7, I have. So I'm going to select 2 parts. Let's say I'm creating contact between this and the green part, and then here I can define the Coulomb friction between those 2 parts. So you have the option to do that. Okay, and then in this same thing, you can also tie it back instead of friction. You can also have once the connected contact is initiated, you can connect that. You can hold down like a kinematic. That would be the different type of interface, which is type 2. I mean type 10. Okay? So you can have friction for your contact. Let's move on to my PPT. So we talk about spot weld. On the spot weld, another thing, the idea I wanted to bring up, you can create spot weld here, right? When you do the analysis, based on your result, what come back to you, you can say, okay, maybe when this part needs to be connected, so you spot weld it. But most of the time, your spot weld information come from design and release engineer. They give you a master weld file that you use to connect those things, your information. So in order to do that, you can bring in your spot weld, you can spot weld, and you can import the spot weld from a file. So this could be your master weld file that came from the designer. And once you load this master weld file, it will put the connection to all the part that according from the design engineer that you have. Now, after you run your analysis and you see a need of adding more weld, you create a weld like we just showed you, and then you export those weld back to a master weld file, and you send it back to the design release engineer. So and then they put it back on their design. Okay. So we have spot weld, and then we also have rigid body creation. Very simple to create rigid body. I'll give you a quick example of rigid body creation. Here I have my, let me do here, if I don't have any rigid body, okay. If I want to create rigid body between those 2 parts, this part and this part, there's a hole here, all right? And I want to rigidize these parts here together instead of spot welding. I can go to HyperGraph here, rigid body, say select the new, give the name, if I want to give the title, RB, okay? And then what they asking me is, okay, because the rigid body will ask you a group of node. You need a group of node And then those group of nodes will be selected, will be considered as a slave node. I can do a circular. All right? I just select those nodes. So what HyperGraph will do, it take all these slave nodes, it compute the center of mass of those slave nodes, and then it put them, what we call the master's node into the center of mass of those slave nodes. Then I save it. If you save it, you can see the rigid body. You see this rigid body I just created? Here is what you have. All the slave node I've selected, and then the master node is put here in the middle, the center of mass of the node, of all the slave nodes. The reason why we do this in RADIOSS or any other tool, when you have a master node, since it take into account the center of mass of those slave nodes, the master node can be moved to the center of mass if your selection was not correct in the center of mass. So we don't want to put a master node on a physical element, shell node, for example. So the master node is put in the space. Okay? So that rigid body is created. So we have all the rigid body. I can display my rigid body through, if I take all these out, I can display rigid body. So HyperGraph will show me all the rigid body that I have in the model. Okay? So that's rigid body creation. We can also create, what else we can create? Type 2, we just mentioned, I talked about type 2 interface, spot weld creation. After you create a spot weld, now I have done my connection through spot weld and rigid body. It's also good, it's a good rule of thumb to always check those information that you have put in. So I go back into my spot weld. If I list my spot weld here, if I say modify, it's going to show me I purposely put those spot welds that are not connected. Because sometimes some spot weld is based on segment, the master segment between. And also he has criteria. I give you the criteria of the spot weld. If I go to spot weld here, it's got a criteria. The spot weld I'm creating into HyperGraph is based on this criteria. It gave me the gap, meaning the gap between the space between the two parts. Also give me the minimum or maximum length of the weld, the minimum length of the weld. It also give me the angle. So based on these criteria, any weld that do not meet the criteria will show here in red. Okay, so I show an example of weld that I'm missing. I say show me. What HyperGraph will show me is show me the weld that is not connected. Where is it? It's going to show it to me right here. So he said this is not connected. If you look at it, so now I need to reconnect this one. So I show this, say show it to me. If I don't like the connection here, I say I have the two part. I go to the location, I pick the element, and I say here. The reason why it's not picking, if you look at it, the gap between is too large. So you can't connect this one. Okay? So you have to find another area to connect. That means this mesh area is bad. It's a bad mesh. There's too much space between those two. How is you connected? All right? So that's what HyperGraph will show you, those in the area where your connection will. Let's look at this, for example. Look how it's connected. It's part welding this. That doesn't make too much sense, right? I purposely did this so that you can see things that we have to check in our model before we run the analysis. Because if I don't check these, you run the analysis, later on you come back and you see your windshield is not attached, you start flying. So those are very important entities to check. I purposely put this one so we can see the effect that we can have when we don't check the quality of our modeling. Okay? So we're moving from connection. We are going to touch on rigid wall creation. It's a vehicle model, right? It's an automotive. So we have to represent the physics on our FEA model. What would be my physics? My vehicle is right on the ground. And then I'm hitting a wall. It could be a full flat wall. It could be a pole. So I need to represent those into my model. So I need to go and create the rigid wall. Let's say my rigid wall I want to create, for example. So I go here. How do I create a rigid wall? So I don't have any. I have a flat wall that I already put on it. But how do I create it? This is this representing the ground. So I go under the load case, and I see rigid wall. I can create a new one. So this one, I'm going to create the front wall. Since my ground wall is already there, and I say, let me, before I go there, let me cancel it, go back and explain you the different type of wall. So my load case, I do have wall. So here, under the creation, you see you have different wall. You have planar wall, which is infinite. You have a cylindrical wall, which we use to create a pole impact, for example. You have spherical, same thing, parallelogram, where you have physical wall you create. If I use a planar wall, for example, I say I want to create a planar wall. So what he's going to give me this window, and he asks me, okay, I need to create my node. First, before I do that, I need to know what is these, how far my view, where can I locate my wall here? I know I'm going to locate the wall somewhere this one. So I want to find the I would say the further node information, so that when I create my wall, I can identify where exactly my wall is. So down here, I just select a node here to see the information of that node, what the node is. If you look at the X, 4,000 something. So my wall should be somewhere near the 4,000 something. So here, I'm going to create my wall, 4,500, I would say. So I go to here and I say, my first point, let's say I'm going to put 46 to 1. And yes, I put 4,600. Okay. And then when I create the wall, I need to create the, I say, group of node. I can select the group of node, or I can also put the distance, the search distance, and then I can put a group of nodes. So let's say I go select my group of node. I go here, set the group of node, I mouse click, and I say I want to select this node. Put it right here, and I pick up these. All right. So basically, if you look at my wall, so my wall will be created here. And then what I'm saying is, I want the wall to be any of these green nodes you see. That's when I select the group of node. If I don't want to select the group of node, I have the option to say I can define the search distance. So you have two options. I can either select the group of node. So what I'm telling my solver to do is any of these green nodes, the rigid wall, when the wall see these green nodes, if you look at the arrow of the wall, the arrow needs to be pointing toward the wall. So any of these nodes should be seen as a slave node. It's like contact. So they should not penetrate this wall. So I have the option to select by window, or I can also select by my slave node by what you call, by search distance. So in that case, I don't need a green node here. I can select by search distance or a group of node selection. And I save it. Now, if I save it, you can see my display. When I yes.
The question is there any penalty for selecting all the nodes versus a smaller subset like you did?
Any
like runtime penalty, I'm assuming. So if you select all the nodes in the model, will that cause the model to run any slower?
Good question. Good question. Yes, every time you select, you select all the node, all the part in the model, it will add a number of elements, because your group of nodes now become the entity. The node inside the group is huge, so the solver have to kind of look for all those node information to make sure they're gonna impact the wall or not. So for this type of analysis, I'm doing a front impact. You're gonna see the result later on. When I crash this vehicle against that wall, nothing happened on the rear side. This rear will never crash and touch the wall. Do I really need to add those nodes in here? That's when we use our engineering judgment when we do the selection. So it's always good to select a certain node. Let's say I'm doing a front impact. So what I'm concerned about here, I'm concerned about the A pillar, and then mostly the B pillar, because the B pillar might also crash but it won't crash to touch the wall. So I can increase this, say maybe put a little bit, let's put another one. So if I put another one, I can increase, but I'm concerned more of where, for front and back, my occupant is sitting over here, right? To the B pillar, that's where I'm concerned. So I don't need really everything on the rear part of the vehicle. So you want to minimize your model size by reducing some of the impact zone where you are more concerned about. Okay?
Another question relates to the wall. Can you move the wall after you've created it? Change the distance between the wall and the car?
Yeah, I can move it. I can move the wall. You just change this distance. Your X, right? So I can move this wall back.
Yeah.
Now, but you don't want to move your wall too far also. Because if you move the wall far, the vehicle had to travel to that distance, that space you create between the wall and the vehicle. It had to take time to run to that level until it touches the wall. So you don't want to move your wall too far. But what we have by experience for a full front impact or end cap, we set the wall maybe about 2-3 meters away from the vehicle. So at that level, otherwise you see your curve. When you draw you plot your curve later on, you will see if you waited 10 millimeters before you touch it, the vehicle is going to travel 10 millimeters, nothing will happen. You are eating time. Okay?
Using a valuable CPU time when you
exactly CPU time. Yes. Okay. So that's the real wall creation. So I create a front wall here. If I don't want it, now this is the front impact analysis. I use a full frontal. I can switch this to a pole impact. So in that case, my wall, instead of creating a planar wall, I can create a cylindrical wall, this one. Then I put the diameter and so forth. Okay, I have the model set up for that, but we just change the wall from planar wall to cylindrical wall, spherical wall, and you have a different impact mode. Okay, let's move on. So that's what we have for wall creation. Then another feature. Let's look at first what we have done. So I have my wall created here. See, I put a huge number of things so it pick up the whole vehicle. I don't need it, so I change it to this one and save. Okay, so I have my wall creation. In HyperGraph, if I hit F5 here, all my wall are created. So I have the floor and then the front wall. Okay, now I have my wall. I have attached all my part. The next thing I need to do is I needed to create this vehicle. I need to apply the speed, the velocity. So I need to create an initial velocity. It's a front impact, so I gave it a load case of initial velocity. So I go to my initial velocity creation. I can create my initial velocity. I give the initial, I give the title. I can leave here, and I put my speed. It's going to be, if I look in here, you got to watch carefully your coordinate system here so you know where you apply the velocity. So I put so here, if I want the vehicle to move, I'm going to be a positive X. So let's say 35 miles per hour, that would be my 1546, right? Okay. And then I say I apply. And I say, okay, where do I want to apply this one? I give the group of nodes. So at this time, I'm going to select everything, okay? Because I want the whole vehicle to move. So I select everything, and I load it. So my velocity is created. If you look at HyperGraph, it's going to show you the direction of that velocity. So which is a good feature for you so you don't miss where your velocity is oriented. If you change this sign to a negative sign, HyperGraph will give you a show you an opposite sign. It's gonna. So those are the good things that you need to make sure you check, and then you have your model tech set up. Okay, so I gave initial velocity. I created my rigid wall. I have created monitor volume so I can have all the airbags, tire, everything inside. The next thing I wanted to do is I need to create contact. Okay, so I'm gonna create my contact. Contact, it will be on the different load cases. We go to load cases. You see contact. Earlier, we have a huge list of contacts, different contact that I have created here. But the main contact on a full vehicle analysis, the main contact you want to create is first you need to create a self-impact. Okay, self-impact means you include all your part into it. So if I go to HyperGraph, we have different type of contact specified in RADIOSS. And those, the main contact that we use is which call it's a multi-user contact type 7. Our contact category on the type. Type 7 is nothing but node to segment. So you have the segment surface against your slave node. So we use this type of contact. We say type 7. Give the title here, and then in HyperGraph, since we designed this for Crash, we make it very simple. I mean, user-friendly. We select here, you have the option to say self-impact. So what it does really, the self-impact is, I'm going to add this, all the vehicle model. So self-impact means if this vehicle crashed against the wall and the part buckle within themselves, they should not penetrate, they should not intersect each other. Because in a physical sense, when your sheet metal touch each other, they don't penetrate each other, right? Or don't intersect unless there's a failure somewhere, crack somewhere. So that's what we do. And RADIOSS use a penalty approach for contact treatment. That's what we do in RADIOSS. So you create this, you have your interface. This interface, we mentioned about friction earlier. The interface, I can define the different stiffness formulation I wanted to do. So on this flag called ISTF, I have different stiffness formulation. If I choose 2, what it does is taking the master segment stiffness plus the slave segment stiffness divided by 2, average basically. So the slave will be your node and the master segment and divided by 2. That stiffness is what the contact we use to manage your contact behavior. So we have different options here to do so. You can save it, say you use minimum. And then we also have different other options if there's any failure criteria. I mean, element fail, you want to make sure that the node that belong to element are failing also are disappearing. Stiffness factor, minimum stiffness, we can define those. The gap, do we want to be 20? So the gap, you give the average gap, let's say 0.3, meaning this is the average gap. You can also choose to have a variable gap. Variable gap would be the best option, but what it does, earlier, if you look at the model, we have almost over 300 parts. So those 300 parts have different thickness. When you use variable gap, what the software we use a different thickness and it calculates the gap for those. And that takes longer time to solve your problem. So usually good to just specify minimum, you use constant gap, you specify the gap, 0.3, 0.7, whatever you want, and the software will calculate the gap against that. Okay? What else I can? Coulomb friction. So the friction will be specified between the 2 parts that come into account. Your friction, if you have a sheet metal, right? So you know steel friction should be within 0.3, 0.2, and so forth. So that's what we have for contact creation. So now I create my contact. I have the contact created. And then the next thing I do, so I have my rigid wall. I have put the initial velocity. I have created contact. I can also add gravity because the vehicle, we want the vehicle to settle on the on your ground. So you can add gravity. So I can close here. Gravity will be on the load cases. I go to gravity creation. I create new gravity. And then here, what do I want? I need to give the gravity function. Put 0. Let's say 9.8. So 0.08981. Okay, so that's my first value. I say yes. And I say maybe go give me 1,000, give me the same thing. Okay, so you put the gravity value and then you want it to add it to. I go here, select everything, select the vehicle model, and say have gravity. Then you have gravity. You want it to have gravity in the model. It's important because you want your vehicle to set out on the ground. So gravity is important to add. In this model, It's the simple one for structural integrity only. We don't have the occupant, but later on you can have occupant in this. You see the mistake I made here, right? I add gravity, but what the direction of my gravity? So we make those mistakes sometimes. I need to switch that gravity. It's under this G, right? It's going down to the ground. So I change it, and then my direction will change. But it needs to be negative. All right? So I put the scale factor here, say a negative scale factor. Okay, now my gravity is oriented the way it should be. So those mistakes, we make them. We make them, and that's why after we finish building the model, we will check the model later on. So we put the gravity. How are we doing with the time, right?
We're doing good. There's a few questions that come up. Most of these, I think, we'll ask you right when you have the model ready to run. But one that came up was, is there any time you wouldn't use gravity?
Anytime I won't use gravity for vehicle analysis, I have to use gravity. Where I won't use gravity, for example? Certain area where I don't think gravity is needed, but that would be a different impact mode. But for a vehicle application, I would need gravity. It's important to use. Now, some other application where I don't need gravity, I would not use gravity. Yeah. Okay. Next question.
The other questions. So one was, can you explain about sections? How to create, where to create in the model, and what would you study using sections?
Oh, very good. Okay. Here's talking back to myself. Okay, and let's say we want to section. Where do I create section? Here, when we run. Okay, this is a unibody, so I will assume we're gonna take this like you have a frame. I take these. So we are doing a front and back, right? I'm gonna take this one. So if I hit this vehicle against the wall, I wanted to monitor the loading that comes in here. You see this here? I'm gonna take this, turn this, let's say this is my front, and I'm gonna reverse this so we can see. I do F5 to my thing will go. Here is my so-called frame. These two pieces here, right? I hit this vehicle against the wall. How much loading go through this frame? So I can see, because if my frame doesn't crush and it buckle, I need to know the loading that is coming to the frame so I can design this frame accordingly to, because the intent of this structural integrity is to protect the occupant. It's very important. So I need to know how much load I have in this one. So here I can create a section, because if I don't create a section, it gives you a local coordinate system where you monitor the information locally. Otherwise, it gives you a global response. Okay. So this front and back, I would create a section here, for example. That's where I can create a section. And where else I can create a section? Let me go back to the full model.
There's multiple sections.
Oh yeah, I can create multiple sections. I can create one section here, section. Especially when you do front and back, sometimes we do what we call sensor analysis. When do we think your airbag need to be deployed? We do those analysis. So I want to create section, multiple section here. Also, I can create section in the, let's say the pillar, to see how much these things crack. I can create section over here. I can create section here. Also, we have what we call, even here, the lower control arm. I can create section to see how much load this lower control arm is getting. Okay, cross member, I can create section. So you can choose to create section depending on your impact mode. For the front impact, I will be more concentrated on the front area where I want to see the section. Also, I can even create section here on the tunnel, right here. Because the occupant is sitting here, I want to see how much loading is getting to that on the tunnel. So I can create a section in those areas. How do I create a section? I go to the load case in HyperGraph, and then I go to what we call data history. The section is on the data history. So I go to data history here, and I have different sections. I can create my section. And then on the section, I have a default section. I can create a section here, specify where I want the section to be localized. So it will create me a coordinate system and give me the information on the section. Okay.
The next question is, can we add 1D elements in type 7 contact?
Very good question. No. As I mentioned earlier, type 7 is node to segment. Surface segment. I'm talking to myself again. Yeah, so it's a node to surface segment. So that being said, 1D element will not be used for type 7. So, but where can you use type 1D element for contact? Things like 1D element, we have a different type of contact, which we call edge contact. So on the edge contact, let's say if I take this part, I'm going to create an edge contact here. I'm going to do self-impact, and I'm going to touch up a little bit of edge impact. When can I use it? Let's say I'm here. I pick up this part. Okay, this part here, and I pick up this part. Maybe I pick these two parts. Okay? And I'll say edge impact. Now, when I create the edge impact, it's using line segment. So on the edge impact, line segment can be a line segment from the 1D element. It can also be line segment from a shell element. So if I pick up a shell element, line segment would be what RADIOSS, the preprocessor will do. It create segment here between the two nodes. Create segment here, create segment here, create segment here. So on the shell element, the 4-node shell element, you have 4 line segment. Okay? And on top of the 4 line segment, you have all the 1D element will have a line segment. So you can imagine, right? How many elements you're going to add into this model when you select your whole full vehicle model and create a line segment? I mean, create a interface type 11, huge. So your 1D element, you use interface type 11 for segment for interface type 11 creation, and then you have to also be localized where you believe or you think there will be an edge impact. Let's say for this, the fender and the door. This area here, you see the edge, right? And since the type 7 is a node to segment, surface segment, if you look at this area, you won't be able to find the segment surface, right? That's why you use line segment or type 11 to create interface 11, and then it will take care of all the 1D element. Okay?
And there's another question for type 7.
Mm-hmm.
When making a type 7 contact for 2 3D elements, do we need to define a contact surface on them?
Beautiful. Okay, that's the beauty of a HyperCrash. If you are proficient in HyperMesh and you were to create your model into HyperMesh, if you deal with a type 7 interface, you need to have physical skin on the solid element, because the way the interface works is, since it's a node to segment, there's no such thing as segment surface on the solid, on the 3D solid. The segment surface is the 2-node, 2D. So you have to create all the faces of those 3D elements, the segment surface, for the solver to manage the contact. But if you're in HyperCrash, you build this in HyperCrash, all you need to do, you don't need to create any skin. Let me just show you a demo. I'm going to display just my solid element. So here's your 3D element. When you go create a contact type 7, for example, in, let's say I'm going to cancel here. Yeah. So my type 7 here, I go type 7. And so my slave would be node, and then my segment would be, if I surface segment, I go here and I create these, select all these, right? And then my slave, I can say select all these. You see, and I save it. This is all you need to do in HyperCrash. HyperCrash will automatically, you see the dummy skin there on the blue. You create those dummy skin, which are dummy segment surface for your contact. So for the 3D element, no. If you depend on where you do, if you do an HyperGraph, you don't need to create a skin. If you do an HyperMesh, you may have to create a fake skin, giving a void element material property and stiffness in that. Okay? We move on. Or any other question? Okay. All right. So now I have done pretty much my. So what I've done, I have connected, create all the material property, put monitor volume. I have put an initial velocity on my load case, gravity. I have put the contact for self-impact. Now, I put the global contact for everything here. Some area I may have some individual contact where I want to monitor some contact forces. I can do those, and I check those in later on, because the global contact is just to protect part within themselves. Okay, so that is done. The next thing I wanted to do is, okay, I have finished setting up pretty much my model. I'm not done completely yet. I'm running this analysis. I want to see some output request. Okay, so I need to put some information in data history, what we call time history, for me to be able to monitor those when I am. This help me do my post-processing. So I need to create some data history. On the data history, you have time history for. So on the time history, you can see here, my time history is on the data history. I have a huge list of the different time history. 3-node shell time history, 4-node brick element time history. I can put all those into time history. What I always recommend to do when you do a full analysis, it's always good to put all your parts in the time history. Yeah. Okay, give me a second here. I'm plugging my machine. Okay. So what I usually do is to add all the part into my time history. So I say part time history. They say yeah. They want me to add them up, and then I go here. I say part. I'm gonna pick all the part in the pick any video part. So I select in the model, and then I will select all these parts into my model, or add them by window. I can do here also. Select everything in the model. So what the solver will do, it lists me all the parts into the model. Because later on, when I do my post-process, let's say this job run, I have the result, something failed, I don't know where it is. So in order for me to identify this, I recommend all the time to add all the parts in the time history. So I'm glad, I'm fine. I say save it. All my parts are in the time history, they are listed. Later on, when I do the post-processing, I'm going to see those parts in the time history. Other thing we do put in the time history are, I create a monitor volume earlier, right? I want to see if my volume, the pressure, everything are here. So I have monitor. When I create a HyperGraph automatically put them in time history. Okay? If I don't want them in time history, I right mouse click here and I say on the data history, I say remove it from the time history. So this won't be in time history. If it's not in time history, later on you wanted to see the pressure of this tire, you don't know. You want to see the volume, you can't. That's why we by default, HyperGraph automatically build these with time history added to it. Another area where we can request time history are interface. All my contact, it's also good to have a time history for all the contact. If I build a contact in HyperGraph automatically put in time history, because later on I want to see, okay, my contact force between two parts or between a wall and a barrier, where can I find it? So we put those in time history. I can put some element in time history, and also what we put in time history are nodes. Because when you run this analysis, you are going to run this against the test. You need to, the idea of FEA is to really predict the future. But sometimes we don't predict right the future, so we have to correlate to the test. They run the test, the physical test, the result come in, our FEA result don't match the physical test. So what are we missing? we go and correlate the tests. So those tests have different channels. Things like if I run front-end pair, I want to see information on A pillar, I want to see information on B pillar, so I pick up some node in the B pillar to monitor the time history. I want to see information on the cover, I check some time history on the cover. Also want to see information on the tunnel, because my occupant is sitting somewhere here, so I pick up some node on the tunnel. I want to also pick up some node here on the front part of the vehicle to see all those loading, what is the information I'm getting from. Yes?
So another question is, are the spot welds or glue elements also included in history or time history parts?
No. The spot weld are not automatically put in the time history, but you can, let's say if I go to spot weld here, you can put them in the time history. You see, this is a, right, you see none. You see, this is, it says stored by a connection type or NTH. If you see here, none, everything, no, right? So if you want to put this spot weld in time history, you can right mouse click here and say spot weld, put it into TH. But by default, we don't put spot weld in time history because there's really no need for it unless you wanted to monitor this weld failure on that. So if I look on my list now, I should have a couple of time spot weld here on the with the yes into it. I think my yes must be somewhere there. I miss it, but I have to save it first. Oh, my HyperGraph stopped.
Oh. Well, at this point, were you needing to go? How much more of the model needs to be set up?
I think I'm done from this level. This level, what I have right now is I'm on the last point. After time history is ready to show what I want to monitor, and then once I'm done with the time history, I am right here. So I'm done with my time history. What I really want to check is the model quality.
There's a good question here. I'm getting to that before you get into there. So the question is, do you have a standard procedure to convert the HM model to a RADIOSS model? Let's assume it has 1D, 2D, 3D elements and contact interface. And I know we showed a HyperCrash, but HyperMesh does have a RADIOSS interface to handle that.
Beautiful. Yes. So, good question. We don't, like we mentioned, if you look at the first slide I showed, I said we have HyperMesh and then we have HyperCrash. HyperCrash was designed for crash and analysis, but HyperMesh is designed for everything. You can do crash, you can do FSI, then everything. So before if let's say I'm working on HyperMesh for this to set up my model. So when I launch HyperMesh give me a profile, user profile. I have different profile here. I can choose RADIOSS 10.0, 11.0, and so forth. So I choose 12.0, right? So now I can build my model here with RADIOSS 12.0. I can create a contact. I don't need to convert anymore. So now that means I'm on RADIOSS profile. So whatever model I write out from here is going to be a RADIOSS model. Okay, that's the question you asked? Yeah. So you have the RADIOSS model from here. There's no conversion between RADIOSS and from HyperMesh to HyperCrash. We had a built-in tool here on put on HyperMesh and HyperCrash where you can go from HyperMesh to HyperCrash to HyperMesh. We have these on the mesh editing. We got here. I can go pick a part. Let's say I want to modify this. HyperCrash is not designed for meshing. It is designed to set up your RADIOSS model or Dyna. So here, if I want to do a mesh modification, I can transfer these and then HyperMesh will launch. I'll see HyperMesh. So now you see my windshield is coming to HyperMesh. I can do the modification here. Let's say I want to delete part, I mean the element. Okay? I delete element, say yes, delete those. Or I'm changing the geometry and I'm done. If I'm satisfied, I'm finished with this one. I can my HyperMesh. I can close my HyperMesh section, and then say he's coming up. So what happened is, give me a second. Okay, come on. Okay. It's freezing here. But okay, but yeah, that's just a small feature I wanted to show you. Don't need to do this.
One more question before we'll take, and then we have to get into post-processing because we're really at the time limit here. And it's great. Definitely, we love all the questions. But the question we have is, can we have a deformable object instead of a rigid wall? And if yes, how do we define interface and constraints for that?
Good question. Give me a minute here. Where's my mesh section? I want to kill this one. I think it's frozen here. Here's my HyperMesh. Okay, yes, I can have a deformable object. Let's say, as a matter of fact, I prepared that for your question, so we can see. I see right here. Give me a minute, it's going to come. So for that reason, I had also prepared a offset deformable barrier model. So that the first one I did was a full end cap or full frontal, but I also have offset deformable barrier. So here's we can do this. This is the 40% deformable barrier. I've ran those three models, the pole impact. So this is deformable. This one, you have the vehicle crash it against the deformable barrier. You can set this one. So so this one you will have the contact. I can have the contact between, between barrier. Let me see my contact. What is this one? It's going to give me the contact in a minute. I think it's this one, V to B, vehicle to barrier. Here's the contact. So this one now, I have, if you look at it, I didn't select the whole vehicle. The point I don't need, I leave them up, but I put the vehicle between, the contact between the barrier and the vehicle. Barrier is my slave because it's softer and a smaller size element, and my vehicle is the master segment. So this is deformable. I'm going to show you the animation a few minutes ago, and in a few minutes, to see how much that barrier deforms. So yes, you can have to be rigid wall only. Okay?
And other tutorials that also show that in?
Yes. We have a tutorial for pole impact, or I don't know if we have an offset model there, but I know the pole impact tutorial in HyperWorks Online help. Okay? Basically, when I do that, all right, if I do that, okay, let's say if I stay in here. Now my model is pretty much done. Let me go back. I'm done my full frontal. I've done, if I look at my PowerPoint, what I wanted to present, quality checker. That's the last one I want to do. I want to emphasize on that one. It's important for me or to the listener. It's not just building the model, but after you finish building the model, before you run the job, I want to emphasize on it. As a support engineer or application engineer, I be in the field. I work on the field a lot, and I see many people finish building their model into preprocessor, HyperMesh, or HyperGraph, and then they submit the job. They don't even check the input there. It's a bad habit. I'm just emphasizing to you, you have to check the quality of the model because you can't guarantee everything you've done right. So HyperGraph have a tool we call model checker. Under the model checker, I have model checker here, and then I also have an interface quality checker. I have the contour checker. I'm going to give you first model checker, and I say run the model checker. So my checker will be done in a minute. So when I go through, you go through my whole model, and it point out, okay, everything looks fine except you have a local coordinate system here that is not too correct. I just first will put that to see. Then I say show me. If I say show me, he's going to show me that coordinate system. You see that coordinate system is here. All right, so that's where I put the coordinate system. If you look at this coordinate system later on, I see the node 1, node 2, and then node 3 is on the same line. So you say, well, okay, right? You say, no, your coordinate system for the revolute joint doesn't seem correct. So you put that information too. Other than that, everything in my model looks pretty much orange. Everything looks good or green. So my quality checker, everything is fine. If I go to my browser here, I have velocity, I have my contact, I have all the other entity that I have available. The next quality I want to check is contact. I create all the contact, right? I want to make sure my contacts are correct. There's no intersection or penetration. Here, I purposely put some intersection. You can look at here. Sometimes these intersections is a bad meshing. This is not me putting this where it's a bad meshing. If you look at here, you see the drum or your brake or your tire here, these two parts are intersecting. Okay, so HyperGraph show you those area where intersection, with different intersection. So these are quality issues, things that we need to check when we run the analysis. We have to make sure everything looks perfectly meshed without any problem. So that's and then the next thing, last quality check that I want to show you is I call a contour check. Under the contour check, I have different attributes. I say show me a Young's modulus. So he's gonna show me, based on my model here, it's gonna show me parts that have smaller Young's modulus. Sometimes it might be a modulus that doesn't make sense. Here is a 20 EPA, megapascal. If I say the 20 here, it's going to show me that part. You see, this part is an aluminum, so that makes sense. Other than that, still you can see 210 to 200 thousand megapascal. So those look okay. The next thing I want to check is density. Okay, you see a density e to the minus 10. Oh, that's that one. It should be within the range of minus 11. I mean minus 9, right? There might be a part with a Young density low. What is that part? It's okay. That makes sense. It's the front part of the barrier of a car here, the bumper form. So yeah, I can have a smaller density. So I check those things. So those are done. Yield stress, same thing. Everything looks fine, and I'm satisfied. Now I'm ready to run I'm ready to submit my model. Okay? So I ran this model, and then I wanted to look at the result. So I'm going to HyperView. So I have two results that will come out of my analysis. If I look in here, I have the 3 analyses I've done, the full frontal that we just talked about. I have, before I go to the HyperView, I ran this analysis. RADIOSS will output you animation that you can use HyperView to post-process your animation. Also, it's called a time history. Remember, we defined the time history data on the data history, interface, monitor volume. So those will be read into HyperGraph. So in HyperGraph, I can see my time history, and then HyperView, I can see my animation. Now, but before I go to this, when I run the analysis, it's also good to check your output file. The first RADIOSS give you 2 files, basically. You can have 1 file or 2. But the first file here called 00 is your input file. If I open this one, this is my input file. You say RADIOSS starter, you give me the version of RADIOSS I'm running, you give me the material, and so forth. So when I run this analysis, this input file, it's going to give me an output file, which we call a 00 out file, where it gives me the information on all the information I have in the model. If I check for time step, if I look for a time step here, it can give you, all right? If I scroll down, I'm going to be brief, quick in here. If I say time step, it's going to give you my brick element time step, and it gave me the element that I have a smaller time step. If I want to do time step control, I can check all those element, spring shell element, and then nodal element time step. So these are values I use for quality check. The main thing I need to look at if I want to be quick on this one is your engine output. This is information important for me before I even go further. I ran the analysis. how the duration of the analysis should be in my engine file, and they give me animation. My first cycle here, if I run a front-end pack, it's always good to check the first cycle. My total energy, kinetic energy, my work external force, and then my mass added. So I need to check these kinetic energy. Does it make sense based on my mass of the vehicle, the initial velocity I gave? If I use my basic, math formula, kinetic energy of 1/2 mv squared, I can make sure that this value makes sense. So now everything looks good. My energy balance, if you look at it, it's pretty good. Negative energy. Okay, and it starts with 1.6%. That's beautiful. Mass, 1% mass. It's a great analysis. Now, from this level, I can go now in the HyperView. So I got my HyperView here. Then I'm HyperView because that output file will not give me anything if I have model that. If I do have what I call. Go here. Where's my where did I put my file? Let me see. Okay, here. So I'm on front-end path. So I'm gonna load my animation. So you can see now this is what I created in the Hyper preprocessor. Front wall, floor wall, and then I'm gonna animate this. So I can see my vehicle crash against the wall. Okay, this one I can look through. I don't see any part flying. I don't have any failure. No part are really flying like they are detached or they're not attached. If I look at him, let me minimize my speed a little bit. If I look in here, maybe it's better off, stop it, and then I can see. All right. So the question I asked earlier on the section, I could have cut a section here and see what the loading by this bracket is getting. So I can see my lower control arm, I don't see it's cracking, so it looks good so far. Okay, my tire, if you can see, my tire at the volume inside, everything looks good from the animation standpoint. But it's also good to check my contour plot. Contour, what did I request? I have requested plastic string. I want to see those plastic string. I can plot those plastic string and I say animate. So it's going to give me some plastic string value. It's going to show me, say, okay, the smallest part, the largest one, 1.7. So it can show me the part. If I look carefully, it show me the part that is giving me the smaller plastic, the larger plastic string. There's somewhere here, you can see that. All right? I can also plot my von Mises stress. Okay, apply. So it's gonna show me the part with the highest von Mises stress. You can see those von Mises stress everywhere on the part. Okay, so from animation standpoint, things looks good so far. No really concern about part flying, so I'm satisfied. Okay, I can load now my HyperGraph. HyperGraph, I don't even have to go anywhere. I can go here, switch it, and have a second plot here. Here to plot my time history. So I go here, and time history, that's what I'm requesting. I go TH, say TH, it's open. Then I want to plot my, see my global energy. Do they make sense? Do I have any, my kinetic energy look good based on what I saw. Hourglass energy is important to check your hourglass energy. Total energy, I check those, and I say, let me move this one away from here, and I say plot. Okay, so I can see, then I can interpret my my analysis here. If I look in here, let me move these things away from here. I can interpret my analysis here. Okay, I don't have any hourglass energy. That means my material, my property, section property I defined. There's no too much hourglass, and my mesh is okay. Total energy, which is the summation of the kinetic and internal energy, look good. It's a front impact analysis, so I should start here. That's my initial kinetic energy I just saw from my output file. And then here where you see the internal energy and kinetic energy crossing, that's pretty much the time where my vehicle rebounds. So I don't need to run a little bit further. I ran to 90 milliseconds here. That's good enough. I could run more, but for a full front impact, I don't need it because my vehicle rebounds around 65, 70 milliseconds. All right, this looks good. I can now go further in detail, make another window if I want to see nodal time history. These are the, remember I asked you the part. I'm going to go here for an example. Go back in here and then turn this one off and plot all the parts. I say all and I say this, for example. It's a kinetic energy. The reason why I say this, remember, you see, everything looks perfect except one part here, which is an engine. So that means the engine part is moving. As a matter of fact, you're in front, right? You hit the vehicle and the engine part's going to move. So this one is showing me also the engine part is moving. The reason why I do this is to see what part is flying. I mean, what part is not accurately designed. Model into my my analysis. Okay. All right. That's pretty much what I have. I can load. Yes.
We do have a couple questions, and I was just holding them off because I wanted to get through showing the basics part of post-processing here. The first question was back related to converting the model. They were asking, they had a follow-up question was, they have a large OptiStruct model in HyperMesh, and how would you suggest converting that? And large means about 2 million elements with 100 components. So,
and you want to convert these to
RADIOSS
block. Very good question. Okay. There's two steps in here. In the OptiStruct model conversion from which is bulk to block, we have a tool built in there we call B2B, the bulk to block, where we take the OptiStruct model and convert it into a RADIOSS block model. That is done into HyperMesh. Okay.
Just quickly, run through how the steps would be.
Let's say I'm on HM. Okay, I have HM. You say it's a large model. It's going to require you some work to do that. Okay, so I'm gonna, let's say I'm here, and so this time my profile will be OptiStruct, right? So I have OptiStruct model, and then I have my OptiStruct model. I don't have anything here, but that's fine. Yeah, I don't have anything here, but that's fine. So then I have this OptiStruct model. Let's say my model is loaded here. I can go to Tool, and then I have a Convert. So on the conversion here, you have OptiStruct to RADIOSS block. So you can do. So you click this, the RADIOSS will do HyperMesh will do a bulk to block, and you do the conversion. You click it, and you run the conversion until it finishes. Once that is done, you can work on HyperMesh. You can bring that model now. Now it's going to be a block because the block profile will be 12. You can bring this back into HyperCrash and build your model there, or you can stay in HyperMesh.
To read in HyperCrash, would you have to export it then to a RADIOSS deck?
Yes. Once you do let's say if you do a bulk to block here, it's going to write out a RADIOSS block format. Then you can read that into HyperCrash. But what I'm saying here, we just show the HyperCrash here because we're doing cross application. You do your bulk to block here. You don't have to go out of HyperMesh. If you're proficient in HyperMesh, you can stay in HyperMesh and do the work in HyperMesh.
Is there anything to look out for when you do that? Is there any OptiStruct type that might cause some problems?
No, well, you have to check your material and make sure because they're going through linear to non-linear material. You have to check those, and but I don't foresee, especially from OptiStruct to RADIOSS, I don't see much.
Okay. Yeah, and going to between the two equivalent solvers, the next thing would be just now all the interfaces and things like that would have to be set up, since that is something you would have in object structure.
Yeah. Okay, next question. Basically, from my presentation standpoint, that's pretty much what I want to show you. I also did the offset impact model here for, the pole impact. So you see the same behavior. Do the same thing. You can plot it also. Okay. So what I did here, the same model, I just removed the front wall and put the pole impact here. Let's say you are hitting an electric pole. Okay. So these are still non-deformable pole. And if I go to the next, I can create another window here and bring you my other.
If you another question is, what would the effects and results? What will be the effects and results if we run the model of intersections?
What is the question?
What will be the effect and the results if we run the model of intersections?
If I understand the question, your section mean submodel. That's what you mean, or what do you mean a section? You mean a cut as
no, intersections.
Oh, the question say if I run it, there's an intersection?
Yeah.
In the model? Okay, good question. When we were in HyperCrash. Okay, when I did a quality check here, it showed me, let's say I show some intersection. Intersection means what? Mean when we mesh a mid-plane surface, mean half of the thickness, that's where our mesh is. If you intersect, that means two mid-plane surfaces are across each other, all right? When you intersect, if I take this example, maybe to better represent it, I think. Yes. This is an example. So when I have intersection before starting, my contact will not be working, because contact is to avoid two parts to cross each other. So before the analysis, I already crossed to each other. So in that case, my contact with let's say in this area, if I want to monitor the contact force between those two pieces, the contact source is already violated. I can't have the correct contact force. So intersection is not acceptable in your analysis. But we don't live in a perfect world. We see a model with an intersection, which I showed you an example here. In the scenario where I see intersection here, and our contact, we have some flag. If I go in here, we have some flag, let's say this one, for example.
But that's if you do your model check beforehand. What would you see in your model if there's intersections?
Okay, in the intersection, if you run the intersection in the model, you will see time step for your contact will drop, because the time step is computed from interface. It is a node. You take mass of the two nodes divided by the stiffness of the contact. So when you have intersection, that means your slave node is already penetrating into the gap of the master segment. So in order for your master segment to push that node out of the gap, you need a higher stiffness. Since your time step is divided by the stiffness, the higher the stiffness get, which is due to the intersection or penetration, the lower your time step get. Then your job can take forever to get you a result. So you want to avoid those.
So if you have also some really small time steps, and there's a potential problem with intersections. Okay.
Exactly.
Another question in crash analysis: if we use SPH, what should we be careful of?
Okay. In the crash analysis, when you do, first of all, you have to know where you use the SPH and the crash model. The crash model where I can foresee the SPH is in your tank, your fuel tank slushing. If you are concerned about fuel tank slushing, remember on the first slide, on one of our slides up here, I show you.
Yeah, or like impact of a bird on a wing or fuselage. That's a crash analysis too. You would use the bird
as SPH. Yes, you use bird as SPH, or you also you will use let's say we just saw the boat ditching, right?
Yeah.
You can use the water as the SPH. Yes. Any other?
Yes, but what should they keep in mind? Is there anything when setting that up?
Oh.
That they should be aware of.
Okay, on the SPH setup, you have to be aware of the what we call the pitch, or the smoothing length. The smoothing length is that's what you use to calculate the time step up for the SPH. So before you build the SPH, first of all you have the volume, which is meshed on 2D shell element. So your SPH particle need to be when you define the diameter of the particle, you need to stay within the smaller size element. So otherwise, you have too many of particle.
Okay.
So you want to stay within that.
And then we also do. I know we have some SPH and ALE tutorial models in our online help, and those should be looked at too for how to approach a model like that. So.
Okay. Your contact, when you create a contact, SPH.
Oh, no, what I'm getting
at Antoine is that we do have some tutorials about SPH models and ALE models in our tutorial, so that'd be another resource there.
Yeah. Okay. Any other question?
No, we are losing some people because we are running late. and a lot of great questions, and we appreciate that. I think if there's nothing else you want to or planning on showing, Antoine, I will just show for 1 minute where for the students here where they can get the free student version, and where there is some very specific training material for them too. But this is was fantastic and definitely a lot of detail here and a lot of good questions that I think that really showed that people have applications and really want to apply this to what they're doing. And I can tell some of them are already applying it. They just needed some more help there.
Okay,
So
thank you.
Yeah.
Thank you for your attention.
Yeah, so great. So thank you, everybody. So what I want to show, so if you go to our website, I know some of you are also from overseas. All of our websites, depending on what language you're in, will be very similar. All you'll need to do is go to our Academia tab, and when you go in there, you can pick on Altair University or go right into the academic program. The Altair University will have training material that you can access to look at how to learn our software. But for using the software, you want to go right into our academic program. And then here, the home page will show things. You can define what country you are, and it'll show you specific news, what's going on. But over here, you can go to software. You see there's free student edition. You click on that. You'll be filling out a form. You'll need your contact information, and you'll be doing a $0 purchase. And just fill that out. We'll get a notification, and we'll be given some other instructions on what you'll need to do next, where to download, and we'll make a license file very specific to your workstation, so you get instructions about that too. The free student version was good for 1 year. If you're a continuing student and need it later, you can reapply again after that expires too. Also, the current version of 13.0 has a 10,000 node limit, and it works primarily with our solvers. So if you want to, if you want to do RADIOSS, or if you want to use OptiStruct, or do linear static or optimization, or MBD or CFD, it'll all be with our solvers, and then it's all packaged together in your download. If you need to use with another software, then you would have to look at our full version, which you will need to either have a license by your university, or if you're a competitive team and we're sponsoring you, you'll get a full license then. If you are part of a formal team that isn't currently using our software, or you're part of a team that's using our software but want their own version. Frequently what happens at universities is that they do have a HyperWorks in their lab, someplace else it's their engineering lab and not your formula lab that you have set up. You might want to get your own version, and it probably would be helpful because then you can run it on your own workstations. So you just go over here, then you want to basically fill out the sponsorship form that you see down here. The local office will then contact you, get your license file, and just go over a few details. The main thing that needs to be done on your end for the free version is that you put a couple of decals on your car for Altair, and then you let us know how you're doing. If things are going well and you would like us, we even have done success stories about different teams, and we're happy to do that if you want to get some more fame about what you guys are doing. Our marketing team will also work with you and maybe put together a case study that we will post. And then we also have, for those who are going to the Formula event in May in Brooklyn, Michigan, we do have the William R. Adam Engineering Excellence Award, and you can apply for that. And basically, fill out the form, and during that event, we will come by and judge what you've submitted, and at the end of the event on Friday evening, we'll award a $1,000 award and a $500 award to the two top teams. Those were the main things I want to cover. I know we covered a ton of material. We do have more training material under the Learning Library, under the Altair University page here. A lot of these are videos, and we do have some archived ones, which are still more the tutorial format. People like that format too, and that's why we have it there. But on our Learning Library, you'll find a lot of webinars and videos here that might be something of interest. Also, one nice thing about if you have the full version of our software, whether it's your competitive team or at your university, we have the complete online help available for you too. So with all the tutorial models and so forth, to keep the student version small in size, so you're not downloading 5 gigabytes. We've taken that out because that itself, all the models and results are over 1 gig. So something we're looking to adding in the future, but current version 13.0 does not have that with it. So you would have to look on our Learning Library. And another nice thing we have for students, we have some free PDF books, some practical aspects of finite element analysis, and additional things for doing structural analysis, multi-body analysis, and even one for crash analysis with RADIOSS. So if you're attending today's session, you probably would like to get this book here. All you need to do is pick on it, fill out the form, who you are, and you'll get an email with a link to that book. So again, thank you so much for your attention today. I know we ran late. It was a great session, great questions, and wish everybody good luck. And if you do have questions about in your student, feel free to go to our support and training, and there's the support form there. We have 2 individuals who monitor the support form, so they usually at latest will get back to you within 12 hours. To a question, but usually they're pretty quick, and it's within hours that they get back to you. So that's where we do ask the students, is to ask all their support questions here. And that's how we're set up. So again, thank you so much. Thank you, Antoine. It was fantastic, and everybody have a great day.